Yeah, so I guess welcome to the first SMLI talk of the semester. So we're going to get back into the swing of doing things after a short hiatus during August. So I guess obviously I'm giving the talk today, and then in, what is it, the 22nd, I forget the date, Kyriakos is going to be doing another talk at the end of the month. So yeah, I'll give him a small shout out about what that's about briefly later in this talk because it's related.
Don't spoil my call.
What's that?
Don't spoil my call.
Oh no, okay. Well, I'll say like 2 words. Yeah, so I guess that's all administratively. I guess sort of some of you may be new, and some of you are probably returning. For those of you who are new, just the idea of these is, it's just undergraduate, graduate students and postdocs just talking about machine learning and the research they've done in machine learning. Sometimes we do tutorials on new topics in machine learning. So that's sort of the gist. It's very low stakes. So I guess that's the gist. So I probably shouldn't gab too long. So I guess with that, I'll start. So today's talk is Decoding Dark Matter Substructure Without Supervision. So this is going to be a talk where I'm utilizing a form of unsupervised machine learning to actually infer the presence of dark matter substructure in an attempt to potentially use that as a mechanism to potentially constrain or even maybe identify what dark matter is. And I'll get into the details, of course. So this is work that I did in collaboration with Professor Alexander and then also some collaborators at Alabama. So let's get right into it, I guess. Oops. There we go. So, if you restrict our lives to just living on Earth, right, and we do our experiments at CERN with colliders, the standard model works great, right? So if you just never looked out into the cosmos, you'd never suspect that we didn't understand everything because quantum field theory works brilliantly, right? There's really not a lot of questions left on the table. But then you have this mysterious thing when you go out and you look into the universe and you see, crap, there's a lot of stuff out there that we don't understand and that we can't explain with our current understanding of physics. And, for those of you who have been to any talks about dark matter before, you guys all know the same story. 1933, Fritz Zwicky looks at the Coma cluster. He infers that, there should be more matter than you can actually see using something as simple as a virial theorem. Then you have another pioneer, Vera Rubin, who goes out with collaborators and measures rotation curves of galaxies and also does essentially the same thing. Says, oh, okay, there's got to be more matter than I'm actually seeing here. So there seems to be a trend. Initially, people didn't, buy into Zwicky because I guess he was crazy. But then there's the real cruncher and really the strongest evidence for dark matter is just when you look at the CMB, right? So if you the strongest evidence is basically the relative power in the second and third peaks of the CMB power spectrum. And you can see that here in this animation where what we're doing is the purple bar is varying the fraction of matter in the universe, and you can definitely see that, or cold dark matter specifically. And you can see the effect that it has, and really that's you can't work your way out of that. You need dark matter. So it's not some imaginary thing. And there's been an entire program in physics for years trying to look for this. I mean, we've been looking at the entirety, literally the entirety of cosmic history and all of space, right? We've been looking from the CMB to CERN, right? We've been looking from now until, moments after beginning of the universe. And we've looked over this entirety for direct detection methods, indirect, looking at colliders. So you've had experiments like IceCube, Fermi, looking for indirect detection, haven't seen anything. Direct detection experiments like Lux, nothing, right? CERN, nothing, right? So there's no hints at exactly what dark matter is. Okay, so usually we work under the assumption that dark matter is something like a WIMP. There are other candidates out there that are maybe a little bit more difficult to detect. So there's also axions. I think axions are interesting. They're well motivated. They solve another problem in physics called the strong CP problem. Of course, I won't get into the details, but there's a bunch of other models about dark matter out there in the market, right? So you have machos, primordial black holes, and all kinds of crazy other things. But then that leaves you the question is, well, what if dark matter is something completely different, something that we actually have no idea, maybe it's something entirely different that we haven't even thought of. Is there a way to sort of start narrowing down these models, throw some of them out, and point us in maybe a direction? So that's sort of where the thinking of this project initially started. Now, what do we know about dark matter? We know that dark matter interacts with gravity, right? So dark matter has mass, right? We know that because that's how we determined it exists in the first place. So the question is there a way that we can actually just use gravity to start constraining these models? So that's, again, sort of the next logical step. Okay, so if we restrict ourselves to looking at a pure gravity approach, and then we look at all of these possible forms of dark matter, is there ways to distinguish them? And then is there a way to maybe use gravity to infer what dark matter might be in sort of a, I'll probably say this word a few times, like a theory agnostic way? Is there a way to do that? And that's actually, we'll get to it in a minute, exactly why we need machine learning to do that. So if you're interested in potentially distinguishing between types of dark matter, one of probably the most distinguishing features is actually its substructure. So different models of dark matter have very, very different types. Well, not always very different, but there are forms of dark matter that have disparate forms of substructure. So for example, warm dark matter has its substructure in smaller scales, so subgalactic scales tends to be washed out compared to more traditional cold dark matter, where you get more cuspy core profiles. But then you have more exotic forms of dark matter, like superfluid dark matter and condensate dark matters, where you get these really, really strange and exotic forms of substructure. So you get these things that are like one-dimensional line densities. Those are called vortices, and you can also get two-dimensional disks. And so those are very strange, those don't make sense. Could those even really be realized in reality? I guess that's one thing. But just the idea is there's all these different types of dark matter out there, and some of them just predict very different types of dark matter, and that could be, they could maybe all be spherical, but maybe they have different scales where a substructure just doesn't exist. Then there's these other crazy ones where they just have really different substructure. And the idea is, well, maybe if we went out there and we were able to use gravity to infer the morphology of the substructure, can we actually now throw some of these out? So that's one idea, and that's one way of thinking. And so the natural avenue to go about doing that is actually using strong lensing as a probe. So when I talk about substructure, I'm specifically talking about substructure in dark matter halos of galaxies. So maybe I jumped ahead a little too quickly, right? So for those of you who don't know, all galaxies are surrounded by this dark matter halo, and that's the main structure of the dark matter halo. But then within that, there might be smaller subhalos that might have this different type of substructure that I was referring to. And so what's a way to get at that in a sort of easy and intuitive way is using strong lensing. So we all know that, matter bends light. So substructure, of course, is going to have an influence on any sort of lensing effect. And in particular, strong lensing is in particular very sensitive, especially in galaxy-galaxy strong lensing. So galaxy-galaxy strong lensing is when you have a background galaxy that is being lensed by a foreground galaxy. And those extended lensing arcs, so what we oftentimes call Einstein rings, are very, very, very sensitive to any type of substructure. So any subhalos that are anywhere near those extended lensing arcs can potentially hold some information about any substructure that is around them. So, there's been a lot of Bayesian analysis, just traditional, something like a maximum likelihood. They assume a model for dark matter, they assume spherical subhalos, some distribution of them, and then basically you do some, crazy state-of-the-art Bayesian analysis, and you go around playing with simulations, and you can get some interesting results, but it isn't always the best. And the big thing is it's very computationally expensive to do anything like this. And then you run into another problem again is, okay, well, what if we're wrong, right? So of course, if you're using a traditional maximum likelihood method, you have to assume a model, right? You have to assume dark matter is like cold dark matter. It has, subhalos or NFW profiles, yada, yada, yada. So you're making a lot of assumptions, and maybe, you say, oh, there isn't substructure, but, maybe there really is. It just isn't based on the model that we're thinking of. So that's sort of a couple flaws, but not their flaws per se, but that's one of maybe a downside. Whereas if you use something like machine learning, where machine learning comes into its own, is that you can do something called unsupervised machine learning. Now I'll get to that in a minute. But in the last year or so, there's been so I'm doing a little bit of self-advertising on this page, I guess. But in the last year or so, there's been a lot of work. There's probably been about 10 to 15 papers out in the last year where people have been using supervised machine learning to identify dark matter, various properties of dark matter. So population statistics, like the slope of the dark matter, distribution of dark matter masses, the dark matter power spectrum slope. Also just basically saying, is there dark matter substructure in this dark matter halo at all? And then also there's a recent paper that Stefan and I did about a year ago, where basically we actually said, okay, can you train a supervised machine learning algorithm where you train it with different types of substructure and simulations, and you say, can you identify between these types of dark matter substructure? And it turns out you actually can. Of course, those might rely on some sort of assumptions that you're making. Of course, there's some of that. But this has been used abound. And then more recently, people have moved to just looking at strong lensing to also looking at other things like tidal streams. And then recently I did a paper with Kyriakos where we looked at astrometric observations. So Kyriakos will be talking about that. I won't say much more because then he'll be upset that I spoil it. But yeah, so there's the literature in cosmology has been exploding recently with machine learning applications, especially in the context of dark matter and identifying it via substructure. But then the question is, okay, if you're doing, I was jumping a slide ahead. Obviously, to do these simulations, I should point out that you're asking, why are these papers using simulations? And that all comes down to the fact that there really aren't a lot of good strong lensing images that are out there, and those that exist, there aren't enough to actually train a machine learning algorithm. So you probably need like 10,000 images to probably train anything that's useful. And in some sense, it doesn't make sense to even train a supervised machine learning algorithm on real data a priori. So you'd probably want to train on simulations and then apply it to the real data, for example. So obviously this relies a lot upon actually simulating. In these cases, we're doing proofs of principles and the work that I was just discussing and that I'll discuss later. This is a proof of principle. We're simulating this data. We're putting in the substructure by hand. So in this case, so I guess I'm sort of foreshadowing here with this is that in our work, we sort of looked at these three cases. So no substructure, which is sort of what the left image shows. And you really should notice that there really is no difference. These are just general images of lensing. You can't actually visually tell whether by eye the effect of substructure, but it's there. So we looked at the cases with no substructure, with vortex substructure, and then just regular particle dark matter subhalo substructure. So that's from left to right. So you can simulate a bunch of those and play around with machine learning algorithms. So this is the result just in one slide of the work that I did from a year ago, where basically you do the supervised analysis. And basically it performs excellent. So the way that you sort of measure, I know we haven't talked about this yet in SMLI yet, we probably should at some point, is actually how do you classify how good a machine learning algorithm is? So oftentimes people use accuracy. I don't think accuracy is a good metric. I'll give you a quick example of why accuracy is not good. Let's say your training set consists of 90% cats, 10% dogs, and then you trained that architecture to classify between the two using that data. I guarantee you can get an architecture that gets 90% accuracy. All it does is classify everything in cat, right? That is 90% accuracy. So that's, if that doesn't make sense, don't worry about it. We'll go over that at some point. But the AUC is a more robust metric, and sort of a way you can think of the AUC as being is if I take random samples from, say, two classes, so one class, it's cats and one class is dogs, what percentage of the time is it going to correctly classify one ahead of the other, right? Because machine learning algorithms do a ranking between its output between two classes or three classes or whatever. So that's a hand-wavy explanation of AUC. And then, okay, so that's the supervised analysis. But the problem with supervised analysis is that it's kind of similar in philosophy to working with sort of just a traditional maximum likelihood analysis, right? Because you have to assume a model, right? So in our case, we're simulating images. We're simulating images based on a model with different types of substructure. And we're training this architecture on those types of images and then trying to distinguish between these different types and see if it can even do it. But that, I don't know, does that do you any good? Probably not. I mean, it's useful to see if the architectures have the power to even extract the information. It's a lot cheaper to do. So that's sort of why it's a good first approach. But for us, the goal was always to do something unsupervised. Could you take a situation where you don't really assume a model of substructure? So in that case, your null hypothesis is just a dark matter halo with no substructure. And then if I now feed it, is there a way that I can now extract some information about any images that I might pass through with substructure? And so to do that, we need to start talking about what unsupervised machine learning algorithms we would want to use. So in our context, since we're looking at strong lensing images, we're dealing with images. So it makes sense to sort of work with something like a CNN. So a natural unsupervised algorithm to go with that kind of can behave like a CNN is a convolutional autoencoder. Now here in this slide, I'm just showing you like what a regular fully connected autoencoder looks like. So autoencoders, of course, fall into this class of unsupervised architectures. So there's three main pieces. I did give a talk maybe a couple months ago, or someone else gave a talk about autoencoders. So I'm not going to spend too much time on this, but feel free, to ask me questions at the end of the talk or whenever, if you want any more clarification. But it comprises of three main components. You have your encoder network, which you can see in blue on the right. And so that actually basically looks just like a regular neural network, right? So in this case, we're looking at a fully connected architecture. And then there's your decoder network, which is sort of, you can think of that as being like a neural network in reverse. And then you have this thing called the bottleneck. Okay, that's some words and some labels and terminology, but intuitively, what does an autoencoder do is an autoencoder basically takes an input and it tries to reproduce that input at the output, right? So for example, I'm going to use the cat analogy. I mean, I guess I feel obliged as a physicist, right, to use cat analogies. So say I take as my input, like image of a cat, and I want to reproduce at the output. I want to reproduce that same exact image of a cat. So I train this architecture to do that. And you're like, well, why is this useful? Well, the reason why it's useful is this thing becomes an absolute expert at creating that class that I've trained it on, right? So it's a complete expert at learning what cats look like. Well, in this case, what we're doing is we're saying, okay, let's train this thing to be a world expert on identifying strong lensing images with no substructure. And then what happens if we pass an image through that has substructure? Can we do anything about that? And then how can we say something about what the substructure might be? And so the natural arena in which to do this is something called anomaly detection. So anomaly detection is a way of using an autoencoder, is probably how I would put it. And you can also do anomaly detection with things that aren't autoencoders. So it isn't exclusive to this. But the idea of anomaly detection is sort of what I just laid out is I train this architecture on this one class. So in this case, we're training it on dark matter with no substructure and learn it very, very well. And of course, when you do this, you can calculate a loss. So any of if any of you have gone or done any machine learning, you know that that's sort of like how you actually go about updating the weights is through the loss. So loss is actually going to be very, very small for images that are consistent with what the architecture was trained on. But then if you start throwing something in that isn't consistent with what it was trained on, the loss is actually going to, on average, be higher. And so you can actually now set a threshold based on your training class, right? The class of data that you train the architecture on, above which anything should be labeled anomalous. And now you're actually able to classify data as being consistent with or not consistent with what you trained on. So this is a very easy way for you to say, what I've just put in here is not consistent with what I put in. Of course, you need to be careful with what you're doing. There could be other systematic effects that you're not accounting for. And, but thankfully in the scenario that we're doing, it's just a proof of principle. We're dealing with simulations. We actually have control with what's going on. So we actually know that the only difference in this case is just between substructure. But actually, if you wanted to apply this in the real world, you'd probably have to be a lot more careful. But that's for future work to figure that out. But just to give you an intuition for like how well these perform, this is what I'm showing you here is reconstructed images. So the top row is showing you simulated strong lensing images. So I don't know what these are, whether there's vortices or substructure or no substructure. They're just randomly chosen. Oh no, sorry, I do know what they are. They're all with no substructure, right? Because that's the point, right? And so what you're seeing on the bottom is the reconstructed version. And you can actually see it does actually quite a good job. You can kind of see like here, maybe this one, I don't know, can you guys see my mouse at all? Okay. So you can see like this one over here, maybe it doesn't do quite a good job, but I should note that this was a preliminary image that I made. So actually the architectures that we actually got our results with are actually much better than what this image was made with. So it actually probably would do a good job in reality. But this is just to give you a flavor for sort of what's happening. I put the image in the top in, and then the one on the bottom is what it's spitting out. And then you can actually quantify that by plotting for your entire test set what the distribution of reconstruction losses. So what I'm showing you is in this work, we trained on 4 different algorithms. So we used an adversarial autoencoder, variational autoencoder, and just a deep convolutional autoencoder. So those were our autoencoders that we used. So those are variations of autoencoders. I won't get into them. That's something that we can get into at like future talks and get into the details. But then we also decided to use a restricted Boltzmann machine, which is a little bit different from an autoencoder, but it sort of has the same philosophy. But what you should be taking away from these images is, so what I'm doing is I'm plotting the loss for each class, right? So there's images with no substructure, and then the images with vortices and with subhalos is in red. And you can see that actually there's some separation between the two. And so what you can now do is you can say, okay, so I'm going to put a threshold somewhere. So like you can imagine putting a threshold right here. You could say, anything like above here, like maybe that's 0.00015 or something like that. You actually calculate this more efficiently, right? In the real world. I'm just saying it for pedagogical purposes now. You can put like a threshold like right here, and you say, everything above here is not consistent with no substructure. And then importantly, what you can now do is you can actually now calculate an ROC curve, and then you can sort of get a understanding for how good of a classifier that this trained algorithm would be. And the first thing that you should sort of notice is we're training on the same simulations that we were before. So before the AUC values, let me just run up here really quick just to remind you. I went too far. The AUC values here are almost near 1. So AUC scores, which is right here, AUC scores near 1 corresponds to basically perfect classification, right? So 1 is perfect classification. So if it's like 0.998, I mean, it screws up a couple times out of the entire training set probably. So you can see that on the same data set that the performance is slightly degraded. And that's actually be expected because it's a little bit harder for these algorithms to actually try to get to the answer that, you know, we're sort of asking it to get to in a way, right? It has to do it on its own. So that's to be expected. So we actually played with 2 different models. The difference between the models isn't important. It's just basically, it's probably obvious that model B is a harder model to deal with, but there is a way that you could bin your data in such a way that you can get model A in the real world. So it's not like, you know, this is a very optimistic situation you couldn't do with model A's performance. Model B is just sort of a more lazy approach to using data. So yeah, so the take home should be, yeah, so you can actually do this. And also I should point out, this is classifying between images that have no substructure and images that do have substructure. And then another way that you can quantify how well you're doing. So there's the AUC value, which is good. But another way that you can quantify how good these autoencoders are doing is the idea is that we want to actually build up, we put in an image and we want to reconstruct that image. So something else that we want to do is maybe we want to also have a measure of like how you know, the fidelity of that reproduction. And so you can do that with something called the Wasserstein Distance. It's also referred to as the Earth Mover Distance. And basically what it is it's a geodesic, or basically the shortest path between probability distributions. And so that's sort of what I'm showing here. So this is a compressed, so the 2D image of a lens has been compressed down to 1 dimension. So you can sort of see like where the center of the lens would be here. And then you sort of do this process of seeing how far away it is from the reconstructed version. So this is the same image, but it's gone through the autoencoder, and this is what's put out at the output. So by sort of comparing how faithful or how close these 2 distributions are, you can sort of get a sense for how good it is beyond simply using an AUC value, where it's sort of based on classification and sort of some of the information has sort of been swept under the hood. So this was like a second consistency check that we wanted to do beyond just using AUC values. And then obviously sort of for us, the natural question was, well, can we distinguish between the 2 types of substructure? So what we ended up doing was we trained our architecture on subhalos, right? Because that's sort of what everyone imagines, that, you know, dark matter halos have subhalos, right? So just normal spherical clumps of dark matter. So we trained our architecture on that data set, and we found that actually it had no constraining power between types of substructure. So you can see that from the distribution of reconstruction losses here. You can see that the vortices in red is basically overlapping with subhalos in blue. So you can't distinguish between them. But what's interesting is that actually the no substructure case has lower reconstruction loss. So sort of what that informed us was that it's doing a good job of getting the general structure, the general morphology of the lens, but it's actually not doing a great job of extracting the effects of substructure. So sort of our first reaction was, well, that sucks, right? Because you can't do anything with that. But then sort of we had the crazy idea, well, what if we looked at, so since this thing is basically just looking at, you know, basically just learning, it's not to say though, of course, that you couldn't find an architecture that could do this, right? So we were using 4 architectures and they weren't actually able to do this, but we have some ideas for maybe an architecture that could extract this signal potentially, or just, you know, separate the 2. So it's not to say you can't do that, but at least in this context, it actually isn't a lost cause, because if you actually, so normally when you calculate a loss, right, for a 2D image, you're actually calculating a loss on a per pixel basis, right? So if you're doing a mean squared error, you're subtracting the reconstructed image from the input image, right? And you're getting an intuition for how far it is. And then you sort of compress all of those little loss per pixel values down to 1 value. Just out of curiosity, we decided to, well, what happens if you just literally plot the, you know, the error, or sorry, the loss without doing that? Is there any information in there if I put it through an architecture that was trained on no substructure and then put images through that had substructure? Is there any information there? Because of course, what's causing the loss to be higher is actually the presence of substructure. So I'm not saying that you can do anything per se with this. This is only just a very preliminary result, but I think it's an interesting result nonetheless. And of course, this is within the regime of simulation, so that obviously you have to keep that in mind. You know, this is very new. I don't know if anyone's ever done anything like this before. But basically, if you actually look at the loss as an image without compressing it for an image that was put through a substructure, you can actually see an imprint of substructure. So let me explain what I'm showing here. Is the left image is a simulation with no substructure. So I passed that through. I passed that through the autoencoder that was trained on no substructure, and this is the loss that comes out. And where you're seeing the brightest pixels here are just corresponding to the brightest part of the lens. So that makes sense, right? The loss is probably going to be kind of worse around there. That makes sense to me. But then if you put an identical simulation, so identical in every single aspect of the simulation, except it has substructure, and identical even so far as the exact mass is the same in both. So basically, you know, here you have the subhalo plus the mass of the vortex. Well, this is, you know, the mass of the halo. The mass of the halo in this image is the mass of the halo minus the mass of the vortex. So this whole thing is the mass of the halo plus the vortex. I hope you understand what I mean. So it really is an apples to apples comparison. And you can sort of see by eye here that you can visually see the impact of a vortex. And of course, in this model, we're doing a proof of principle. It's a toy model. We're simulating these, you know, crazy one-dimensional substructure you can get from superfluid dark matter by one-dimensional lines. Of course, that's not how they would be in the real world, but, you know, we're dealing in a proof of principle, of course. But what you should be able to take home is you can actually visually see the imprint of that vortex, right? You can see, I'm plotting here, this is the same image as this image, but just with the vortex position labeled in red. And you can visually see that, you know, there's a hint of something going on there. How this could be used, how it couldn't, I don't know. But I think it's an interesting thing to point out and put out there, that maybe there's a way to use this somehow to extract the morphology of dark matter. I guess what I'm saying is if you went out there and you saw this signature, right, and you did a more robust analysis, that might be a smoking flag that maybe dark matter isn't something like regular cold dark matter. Maybe it is kind of like a superfluid. So that's sort of maybe a direction to go. Obviously needs more thought, needs more work. But yeah, so that's my talk, I guess. I'm open to take any questions about anything.
Hi, Michael. Can I ask a question?
Absolutely, yes.
So can you do the separation between models in a double step? For example, you train your autoencoder or no substructure, and then with the anomaly detection, you can separate whether there is substructure or not. Can you have a second autoencoder which then is going to be model dependent, and you can train it on like CDM dark matter?
Yeah, you could of course do that, right? You could imagine just creating, because the beauty of once you have one of these things trained, right, it takes, you know, literally microseconds or nanoseconds or whatever to get your result. So you could just imagine training a bunch of these things, answering all kinds of questions, you know,
Exactly.
you want, just like that. And sort of where my vision was initially before I came up with this last sort of idea, right? So maybe there is an imprint of substructure somewhere there. But even when there is no substructure, when you can't classify between them or distinguish between them, I think an interesting use for an autoencoder in the context of strong lensing is sort of like your first step approach. Find what the most anomalous strong lensing images are, and then pass that off to something like maybe your more traditional, you know, some maximum likelihood analysis. What's the thing that's most likely to actually have a signal that I can extract?
Exactly.
And do that very cheaply and do that very quickly. You know, you could put 100,000 images through this thing and like rank them in, you know, probably minutes.
Exactly.
So yeah, that's sort of like one direction you could definitely go with this. And of course, I should also state that obviously a natural direction maybe to go with this is sort of do the inverse problem where you train on the real images, right? So that's what you would do if you had enough images. And then maybe the idea in that case is now you throw simulated images in and just keep tweaking them and tweaking them and tweaking them until the fidelity of the simulation is consistent with your data. And then maybe you're able to extract information that way. So that's another direction you can go, but of course we can't do that. There's not the data for that.
Wouldn't that be a little bit more computationally expensive in some sense? Because the way you're doing it now, you can tell people, oh, there is substructure there. You don't necessarily can tell them what kind of substructure is, but the other way around, you will necessarily have to learn the specific substructure.
Of course. But I think what that would do for you is that you actually do extract the information that's relevant to substructure in that way, where you can't do that with any other method that at least I'm aware of. Or maybe I'm just being stupid somewhere and I'm not thinking about it properly. But I see that, you know, if I train it on real data, I can actually encode the real information and I can calculate, you know, distribution of reconstruction losses. And if I can build high enough fidelity simulations and I can get my loss down where it's basically consistent for every simulation I make with my input, then it's consistent. But yeah, then of course you run into the problem. Well, what if you're, you know, what if the effective lensing is actually, or substructure is subthreshold and it just doesn't show up? I guess there's also that.
Okay, thanks.
I did have one question. I think it's kind of adjacent to what Kyriakos was just asking, actually. And maybe
Sure.
you already answered this in him asking it, but if you're just thinking forward, if you're going to be training this on real data, say that there is some form of substructure present in these lensing profiles that you're going to get from actual data from, I don't know, whatever instrument is observing these arcs. How would you can't necessarily apply this same logic and say, I've now trained on a data set that contains no substructure. Let me put something that I think might have substructure through and see what comes out if there's already substructure present in the data you're training on.
Oh yeah, I see what you're saying. So if you train on something with substructure, then trying to see if there is something, or sorry, no, I guess maybe, do you want to can you say that again? Sorry.
Yeah, no, sorry. I think I presented that in a very confusing way. So sort of the logic that you presented here for this flow of experiments was, I have simulated data sets that contain lensing profiles for galaxy clusters with no dark matter substructure. And then you can use that as a tool. So you say, okay, now I've trained it on these things with no dark matter substructure. If I throw something through, I can identify an anomaly, and I can say that maybe there is some dark matter substructure there in some form. But if it's the case that there is dark matter substructure in the lensing profiles that we observe in actual data, I guess how would you have to transform your analysis? Because if you're training on the real data with lensing profiles that have come from dark matter substructure, that's going to change how you have to tackle this problem. No?
Yeah, so so I guess you're right in a way that maybe I didn't make it clear enough. Yeah, it's a completely different analysis and a completely different line of thinking. In that case, so in that case, how I envision, if you were to, so maybe I shouldn't have mentioned it, because maybe it's a little confusing. Is in the case where you're training an autoencoder on real data, how I envision that is it's sort of like maybe it's a bad phrase to use, but like a theory killer or model killer, right? So you actually train this thing to actually learn, sort of like what I was mentioning earlier with cats, right? You train this thing to actually really learn the structure of this given class. So in this case, the class is, well, what are real strong lensing images, right? And you train this thing to incredible, to the point where it does a great job of doing this. Whether you can do that or not, I guess, is one thing. And then the idea would be you feed in simulations with various, different types of substructure or different assumptions and different backgrounds and whatnot to try to get the loss of that ensemble of simulations that you sort of envision to be consistent with the real data, which is, that's quite different from what I presented here, which is saying, okay, if I train on something with no substructure and then I put in a real lensing image, can I extract that signal somehow? So yeah, they're two completely different things. And the only reason why we're doing it this way in this work is because there aren't enough real lensing images to actually do anything with. I don't know if that answers your question.
Yeah, no, I think that does. But yeah, no, this is really cool. I think this is really interesting.
Glad to hear it. Any other questions?
I just want to clarify. So you trained your networks on simulations first and then compared to actual observations?
Okay, so so the context of the paper that we put out is based completely on simulations. Although I will admit we did put real data through it. I will not say what happened because I don't have my confidence level in the results is not high because, of course, I think we're very much working with the toy model here, right? It's just to see if it can work in these simplifying situations, then it has a chance of maybe working if you spent more time on it and thinking about more of the details. So I'm not going to read into what that means. But in this context, we're working in a purely, simulated environment where we actually have all the control, right? So we know for a fact that our images with no substructure are identical to the images with substructure in every single aspect, except for the fact that one image has substructure. So it's like, yeah, in this idealized case, does it even work at all? It's possible that it wouldn't work. And I'm sure in some models of dark matter, you might not even be able to. The signal for substructure is probably subthreshold for some models, potentially. Any other questions? Okay.
Sorry, Michael. One last question.
Oh, sure. Go for it.
Have you considered other kinds of lensing, like micro lensing?
Yeah, I mean, you could probably do that. Yeah. But I think, yeah, I mean, it's probably not as sensitive as Einstein rings, though. But I mean, it's definitely possibly, yeah. I mean, there's a lot of other avenues that you could, go down, and that's probably one of them. Yeah, I haven't thought about that in any detail.
Okay.
Okay. Well, if there's no more questions, I guess we can adjourn for today. But I just want to again say that Kyriakos will be giving a presentation in a few weeks, so be on the lookout for that. I think it's like the 22nd or something. Let me get the date right. Yeah, it's the 22nd. So 22nd, same time. There should be an email out about it. So yeah, I think you guys will like that. But yeah, so thanks for coming to the talk, and I guess look forward to seeing you all here throughout the semester.
Thank you, Michael.
Yeah.
Thank you very much.